Alright, so I'm going to lecture on section 3.4. There's piecewise defined functions, and I hope it's an easy-ish section. It's not intended to be horrible. This section is functions that are defined in parts, or piecewise defined functions. Let me try to motivate why we might have to create one function and give it parts. If I wanted to, let's say, create a function that can be used to find out how much you make in a week, it might not be able to do that. You might not be able to do this with one equation. For instance, let's say that if you work between 0 and 40 hours in a week, let's say your pay rate is $10 per hour. But if you work more than 40 hours per week, say anything over 40 hours, you get time and a half, which is $15 per hour. I couldn't make one function to figure out your pay because your pay rate is different for the amount of hours work. And I could define a piecewise function that would do this. So I'm going to create one function and have two pieces. The first piece would say my rate is $10 times the number of hours I work, where x is the number of hours I work, provided x is less than or equal to 40. So if I worked 30 hours, I'd plug 30 in for that x, and I'd find that I made $300. If I worked 40 hours, it would tell me I made $400. If I worked 50 hours, and I plugged 50 in for this 10, I'd go 10 times 50, and it would only say I made $500, which wouldn't be true because I'd get some overtime. So I need to come up with a function for if I work less than 40 hours, and then a function for if I work more than 40 hours, or a piece for if I work more than 40 hours, because my pay rates change. And if I work more than 40 hours, my pay is going to be this. It's going to be the $400 I get for working the 40 hours, which is $10 per hour times 40 hours, plus $15 per hour for any overtime. And the overtime is going to be the number of hours I work over 40 hours, or the number of hours I work minus 40. So for this function right here, if I say x equals 20 and I work 20 hours, I'd look at the function and I'd plug 20 into this, because this function is appropriate if I work 40 or less hours. If I work 20 hours, I'd say my pay is going to be 10 times 20, or 200. This function down here is going to be something I use if I work more than 40 hours. And I'll do this. Let's say I work 50 hours. Well, if I work 50 hours and I didn't have a function, I'd go like this. I'd go, I worked 40 hours at $10 per hour, which gives me $400 regular pay. And then I worked 10 hours of overtime at $15 per hour. That would give me $150 worth of overtime pay. My pay would be $550. This equation right here will compute the pay without having to do it in two parts. This equation is used for my overtime pay. If I plug 50 hours in for that x, my pay would be 400 plus 15. And I plug 15 for that times 50 minus 40. And I'd go 400 plus 15. 50 minus 40 is 10. That's going to give me 400 plus 150, and that's the $550. So this is a piecewise function to calculate somebody's earnings if they get overtime pay. Granted, it's hardly worth making a function defined in pieces to compute your pay, because you can do that without a function. But this is just, trying to give you a concrete example of when it might make sense to define a function in pieces. It makes sense to define a function in pieces if for different values of x, it needs a different equation, essentially. So the beginning problems in this section just give me a function that's defined in either 2 or 3 pieces, and they want me to learn how to use the function, how to plug numbers into the function. And it's not particularly difficult once you get the hang of it. It might be a little tricky for the first couple that I do. So problem 2 is a piecewise defined function, and it very specifically says f of x is equal to x minus 5 for any value of x that's less than or equal to 5, but it's equal to 2x minus 4 for any value of x greater than 5. Part A wants me to find f of 0, and I look now at these criteria, and this number 0. If I put 0 into the top inequality for x and 0 into the bottom inequality for x, one of those two statements is going to be true. The reason I'm plugging in 0 is because I want to find out what f of 0 is, and one of the two is going to be false. The x here that I can plug 0 in and get a true statement is the part of the function I need to plug it in. And when I look at this, the top statement, it is true that 0 is less than or equal to 5. It's false that 0 is greater than 5. So I'm going to plug this 0 into the x minus 5 function. I'm going to say f of 0 is 0 minus 5, which is negative 5. So my answer to number 2a is going to say f of 0 equals negative 5. If you plugged it into the bottom function, the answer that you get is not going to be correct, because the bottom function is only good for values of x that are strictly bigger than 5. I do the same thing for part B. For part B, I want to look at the criterias. The x is less than or equal to 5, and the x is greater than 5 that are after how the function's defined. After the definition of function, it tells you when the piece is useful. If I plug 5 in for the top x, after that if, I get 5 is less than or equal to 5, and for the bottom, I get 5 is greater than 5. It can't be the case that both of these is true. Only one of the two is true, and the true one is where you get the level that you're going to put the x in. And it's not true that 5 is greater than 5 because it's not greater than, but it is true that 5 is less than or equal to 5 because it's equal. So I'm going to plug the 5 into the top x and say f of 5 is 5 minus 5. I'm going to write 0 for my answer. So for part B of number 2, I'm going to say f of 5 equals 0. For part C, I want to figure out which piece to plug 6 in. If I look at the x as less than or equal to 5 after the if I plug 6 in for that x, I get the statement 6 is less than or equal to 5. If I look at the bottom if, I plug in 6 for x, I get 6 is greater than 5. It's going to be only the case that one of these is true and the other is false. The top one is false because 6 is not bigger than or less than or equal to 5. It is true, the bottom one, that 6 is greater than 5. So when this value of x, 6, I'll plug into the bottom piece and get 2 times 6 minus 4, which is going to be 12 minus 4. And my answer to part C is that f of 6 is going to be 8. So each of the first 6 problems has the same sort of flavor. It's going to have a function that's defined with either 2 or 3 pieces, and after each piece, there's going to be an if to tell me when that piece is allowed to be used, and then I'm going to be asked to find out which of the pieces to plug the value for x in, essentially. And my answer is just going to be a number. So 4 is a function. It's defined with 3 pieces as opposed to 2. The first number I want to put into this function for x is 0, and I have to decide between the 3 choices after the ifs, if I'm plugging it into the top one, the middle one, or the bottom one. And only one of these can be true. So when I put x for that 0, I get 0 is less than or equal to 0. That's a true statement because 0 is equal to 0. So this is true if I have a number that's less than 0 or equal to 0. Because that's a true statement, the other two must be false. I don't need to check the other two. I'm going to plug this value of 0 into the top piece and say g of 0 is 2 times 0, and 2 times 0 is 0. So my answer for part A is going to be g of 0 equals to 0. For part B, for g of 3, same deal. I have to look at the piece x is less than or equal to 0, which is when the top piece is usable. If x was 3, it's not the case that 3 is less than 0. That's a false statement, so I'm not going to use the top function. The middle function is used for x between 0 but not equal to 0 and 3 and possibly equal to 3. This says x is greater than 0 and less than or equal to 3. If I plug 3 in for this part is true that 0 is less than 3. And this part is true that 3 is less than or equal to 3 because it's equal to 3. Because this statement is a true statement that 0 is less than 3 and 3 is less than or equal to 3. I'm going to plug the 3 into the middle equation, or the middle piece. The middle piece is just g of x equal to x. There's not going to be any algebra to do there because I'm just going to plug in a 3 for the x and I'm done. That's the easiest function to plug in for. The last value I want to try to plug in is -2. So I'll look one piece at a time. The first piece is used for x is less than or equal to 0. If I change this x to -2, I ask myself, is that a true statement? If it's a true statement, I stop and I plug x into the top piece. If it's a false statement, I'll move down to the second piece and see if I can create a true statement. If I can, then I'll, whatever I get a true one, I stop. And because this statement right here is true, -2 is less than or equal to 0, I'm going to plug this -2 into the top piece. I'm going to say g of -2 is 2 times -2, which is going to be -4. My answer for part C of number 4 is g of -2 equals to -4. Six is a little more complicated. I see the squares, which are some parabolas, but it hardly matters for this particular exercise. So immediately, part A wants me to find out which one of the 3 pieces to plug 2 in for. The first definition, the top definition I use if I plug 2 in for x and get a true statement. So if I take this statement, x is less than 2, and plug 2 into it, if that was true, I would plug 2 into 2x squared minus 3. But it's not the case that 2 is less than 2. 2 is equal to 2. That's no good. The middle one is good if 2 is less than or equal to x, which is less than or equal to 4. If I change that x to a 2, I get the statement 2 is less than or equal to 2, and 2 is less than or equal to 4, so I need both to be true. This is a true statement right here that 2 is less than or equal to 2 because 2 is equal to 2, so it satisfies the or equal to part. And this statement is also true that 2 is less than or equal to 4 because it satisfies the less than part. So the middle piece is true. So I'm going to plug this 2 into the x squared, and I'm going to say k of 2 equals 2 squared, and my answer to 6a is going to be k of 2 equal to 4. So for each one of the problems in number 6, the value that's in the parentheses is only going to go into one of the pieces, the top, the middle, or the bottom piece. To figure out what piece it goes into, I look after the word if and see where my true statement is. So for this part B, I look at the first criteria, x is less than 2. For 4 is not less than 2, so I'm not going to plug 4 into the top piece. For the middle piece, I'm going to use it if this statement is true, 2 is less than or equal to x is less than or equal to 4. If I plug 4 in for this x, this is a true statement, 2 is less than or equal to 4. It's true because 2 is less than 4. And this next statement that says 4 is less than or equal to 4, this is also a true statement. It's true because 4 is equal to 4. Because both inequalities in this string are true, I'm going to plug 4 into the middle inequality again. And when I do that, I'm just going to go 4 squared. I don't really need a parentheses there, but it's not wrong to plug it in. My answer to part B is going to be k of 4 equals to 16. The last number I need to look at is 5, and I look at the pieces one at a time. If I plug 5 into the top criteria, and I look at the statement, is 5 less than 2? That's false. 5 is not less than 2, so I'm not going to use the top one. If I plug it into the middle one, 2 is less than or equal to x is less than or equal to 4, I'd get 2 is less than or equal to 5. That's a true statement, but this next statement, 5 is less than or equal to 4, is not true. So both, and the middle one, both statements have to be true. It is true that 2 is less than or equal to 5, but it's not true that 5 is less than or equal to 4 because 5 is greater than 4. So I won't use the middle one, which must mean I have to use the bottom one. The bottom one gives me the statement x is greater, the criteria that x is greater than 4. If I plug a 5 in for that x, I get 5 is greater than 4. That's a true statement. So I need to plug in 5 into the bottom statement, or the bottom piece. I'm going to go 5 times 5 minus 7, which is going to be 25 minus 7, which is 18. So the answer to part C is k of 5 equals to 18. So the first 6 problems just get me used to plugging numbers into piecewise functions. The next few problems have me do graphs of piece functions, and they're not terribly hard to do. My graphs are probably going to be a bit segmented or disjointed unless the pieces happen to connect. So when I go to graph these things, I'm going to do multiple graphs. But only kind of part of a graph. So problem 8 wants me to graph 2 pieces. It wants me to graph the function f of x equals x minus 5, but only when x is less than or equal to 5. And it wants me to graph f of x equal to 2x minus 4, but only when x is greater than 5. When I do these graphs, I first look at the pieces and decide what shapes they are. Each of these pieces is going to graph to be a line. These pieces don't have squares, and my graph is going to be a straight line for if I'm graphing x minus 5, as well as if I'm graphing 2x minus 4. There are many ways to graph lines, but in piecewise functions, the way that makes sense is to plot points that you're allowed to plot. And very specifically, for each one of these functions, I'm going to plot and I'm going to make a table. The very first number in my table is going to be the border number. In the top function, 5 is the extreme value. I can't put a number bigger than or equal to 5. And in the bottom one, I have to plug in only numbers bigger than 5. But I'm going to cheat and plug 5 in because somehow it's going to show up on my graph nicely. When I go to graph a line, I like to do more than 2 points. 2 points is the minimum, but I'm going to do 3. So I'm going to plot each of these lines by just finding 3 points and connecting the points, and I'll do it in a proper way so that the function is fitting the part of the graph it's supposed to fit. So for this top function, I'm only allowed to plug in numbers less than or equal to 5. So I'm not going to go 5, 6, 7. I'm going to go 5, 4, 3 for my x's, and then I'm going to get the y's, or f of x's, that correspond. I'm going to get points. I'm going to plot the points. I'm going to connect a line, make a line from those points. I'm going to be careful of how I show that on my graph because of this whole piece function. I can't just graph like I might normally graph. The next function is only good for values greater than 5. Technically, I'm not allowed to plug 5 in it, but 5 is going to be a boundary that's going to be important. And for this function, I'm going to plug the boundary number and then numbers greater than the boundary number in to get my y's. So now I'm going to find I have two tables. Each table is going to generate 3 points. The points are going to fall in a line, and I'm just going to get the y's. For the first value, I'm going to plug 5 in. I'm going to go f of 5 equals 5 minus 5. 5 minus 5 is 0. So one point I'm going to plot is going to be the point 5, 0 for that top function. And then if I plug 4 in, I get f of 4 is 4 minus 5, which is negative 1. So another point I'm going to plot is the point 4, negative 1. And the last point I'm going to plot for the top piece is f of 3 equals 3 minus 5, and 3 minus 5 is negative 2. I'm going to plot those. So let me plot those points quickly. I'm going to plot the point 5, 0, which is an x-intercept actually, and then the point 4, negative 1. So I go right 4, down 1, and then 3, negative 2. It should happen that if I did this properly, that my points are going to line up perfectly on a line. And generally, when I draw a graph, I make my line go forever in both directions. This graph needs to stop at the end point because I'm not allowed to draw values of past 5 on the past x equal to 5. Because I'm only drawing the portion of the graph up to this point. So this point is going to be the right end of my graph. So this is going to be the right edge of my graph. I'll do the same thing for the second function, except the boundary is going to be the left edge of my graph. So I'm going to plug 5 in for x. I'm going to go 2 times 5 minus 4, plugging in 5 for that x. This gives me 10 minus 4, which is going to be 6. When I go to graph this function, the very first point I'm going to graph is the point 5, 6. I'm going to do something different because the 5 doesn't have an or equal to. I'm going to denote this point with an open circle, and that tells me that I wasn't allowed to put 5 in, but I can plug in any number bigger than 5 in. And in the last graph, I did 5 with a closed circle because the 5 had an or equals with it. Now I'm going to plug in 6 and go 2 times 6 minus 4, which is 12 minus 4, which is 8. And then do 7. Oh, that's going to give me the point 6, 8. That's going to get a solid circle because it's not a boundary point. It's not an issue. And then I'm going to go 2 times 7 minus 4, which is 14 minus 4, which is 10. And the last point I'm going to plot is the point 7, 10. So I'm going to graph 3 points, 5, 6, with an open as opposed to a closed circle because of no or equal to on the inequality, 6, 8, and 7, 10. And the point 5, 6, because it's at the boundary of how the piece is defined, it's going to be an edge. In this case, it's going to be the left edge. 4, 5, 6, 7, 8, 9, 10. So I'm going to graph the point 5, 6 with an open circle, and then 6, 8 with a closed circle, and then 7, 10 with a closed circle. And I know the graph forms a line, so I'm going to connect a line. The right edge is allowed to go on forever. The left edge has to stop at 5 because this function is only good for values of x bigger than 5. And this would be a properly graphed function, or a picture of this function f of x that's defined in pieces. So I made a set of points for the top piece, a set of points for the bottom piece. My top piece stopped at 5 on the x-axis. My bottom piece started at x equal to 5. My top piece at x equal to 5 my top piece had a closed circle because of the or equal to at the 5. My bottom piece at the point 5, 6 had an open circle because that inequality didn't have an or equal to. And that's the entire graph. Ten wants me to graph a function that has 3 pieces. I'll do them the same way. I'm going to graph the function g of x equals to 2x. I'm going to make sure that graph showed up just in case. I wasn't looking to see if I had something blacked out. So just in case, I had the paper down too low. That's the picture that you might have not seen the bottom for. So for problem 10, I'm going to graph g of x equal to 2x when x is less than or equal to 0. This is going to also be a line because there's no square. When I do this graph, I'm going to get three values of x. 0 is going to be the biggest value. And then I'm going to pick numbers less than 0, -1 and -2. So for the top piece, it's going to draw to be a line. The line's going to stop at this point. This point right here, whatever it comes out to be, is going to be the right edge of my graph. And let me just do that now to get that piece part done. And then I'll move to the middle piece, and then the last piece. So I'm going to plug in 0 for x, and I get 2 times 0, which is 0. The first point I'm going to plot is the point 0, 0. Because of the or equal to on this 0, I'm going to get a solid dot as opposed to an open. And then when I plug in -1, I get 2 times -1, which is -2. The next point I'm going to plot is the point -1, -2. And the last point that I'm going to plot to finish up the line, I get by plugging -2 in for this x, and that'll give me -4. And that's going to be -2, -4. So the top piece is going to look like this. I have the point 0, 0, the point -1, -2, the point -2, -4. It's a line, and the line stops at 0. That's the right edge of the graph. Done with the top piece. Now I'm going to do the middle piece. The middle piece of g is g of x equals x plus 1. I want to do it with 3 points. I have to use, because there's 2 values of x here, I have to use both the beginning boundary and the end boundary. The beginning boundary is 0. The end boundary is 3. I like to do this with 3 points. I need some other number between 0 and 3. Either 1 or 2 would be the ones that make sense. I'm going to plug in 1 because it's easy for me. And I'm going to plot this. I'm going to plot the 3 points. They're going to connect to be a line. Then I have to be careful about my open and closed circles. So let me figure out what the y's are first of all. When I plug 0 into 0 plus 1, I get 0 plus 1, which is 1. That's going to give me the point 0, 1. And when I look at this inequality, the 0 doesn't have an or equal to with it. So when I graph this, I'm going to get an open circle. 1 isn't a boundary. A boundary point will always get a closed circle. When I plug 1 in for that x, I get 1 plus 1, which is 2. That's going to give me the point 1, 2. That's going to be a closed circle. And then the last thing I'm going to plug in is 3, which I plug into that x. I get 3 plus 1 is 4. So I'm going to plot the 3, 4. It's a boundary point. I have to decide whether it's an open or closed circle. I look at the piece, how it's defined, and it says for x less than or equal to 3. The less than or equal to, the or equal to part, makes this circle a solid circle. So the middle piece is just going to be a line segment that doesn't go on forever. It's just the middle half of the graph. So let me plot these points. First point, 0, 1, open circle. Second point, 1, 2, closed circle. Third point, 2, 3, 4, and they should line up on a line, and it stops right here. It doesn't go on. This middle segment only goes between these 2 points. It doesn't go beyond these 2 points. The first graph had a left edge, but it had a right edge, but not a left edge. This open circle at 0, 1 is the left edge of this graph, and the solid circle at 3, 4 is the right edge, because this middle piece is only good for values of x between 0 and 3. Now I'll work at the bottom piece. The bottom piece is g of x equals -5x. I'm afraid this isn't going to fit on my window so much. I'm going to have to maybe extend my paper a little bit. And this says this is good for x is greater than 3. I'm going to make a table. The boundary number 3 needs to be the first number in my table. And then after it, I'm going to put 2 numbers bigger than 3, which I'm going to write as 4 and 5. I'm going to get 3 y values, which would be 3 points. The first point, I'm going to plug in 3 for this x. I'll go negative 5 times 3 is negative 15. So for this graph, I'm going to graph the point 3, negative 15 for the third piece. Because there's not an or equal to, I'm going to get an open circle. And this is going to be the left edge of this particular graph, this piece. When I plug in 4, I get negative 5 times 4, which is negative 20. The next piece I'm going to plot is the point 4, negative 20. And the last piece I'm going to plot is the point, I plug in negative 5 times 5, I get 5, negative 25. And I'm going to plot those points. I way don't have room, so I'm going to extend I'm going to cheat, bring my graph onto 2 pages, and try to find room for these papers. So this is 1, 2, this is 3, and then I need to make something and call it negative 15. And that point 3, negative 15, I draw with an open circle. It's the left edge, or the beginning of this graph. And then I need 4, and then I'm going to call something negative 20. And I need 5, and then I need to call something negative 25. And this should form a line. And this graph is going to look like that. It goes on forever to the right because the x is greater than 3 is unbounded. So my graph has three disjointed pieces. It can happen that the pieces connect. I tried to make the pieces not connect so you can kind of see the individual pieces easier. All right, last one of these graphs that we get to do. It's also a 3-piece one. This one, there's some squares, and when we have squares, the graphs are going to be parabolas, but we're only going to see a segment of the graph. And when we only see a segment of the graph, we might not see the vertex, but we're going to put a little bend into the graphs. So I'm going to do the same thing. I'm going to graph with 3 points, but the top 2 in number 12, I'm going to get a little curve. I'm not going to get straight lines. This x squared would make the whole graph be a parabola, which means I get curved edges as opposed to straight edges. Similarly, the middle one, when I plot my 3 points and connect them, I'm going to connect them with a slightly curved graph as opposed to a solid straight line. And then the last one, the 5x minus 7, I will, it's a straight line. So let me think how to do this. So for the first function, k of x equals 2x squared minus 3. I'm told to plug in values less than 2. I'm going to plug in 3 values for x, 2, and then numbers less than 2, 1 and 0. 2 is going to be the right edge of my graph, and it's going to get an open circle because there isn't an or equal to. So now I find out the y's for this. I'm going to go 2 times 2 squared minus 3. That's going to be 2 times 4 minus 3, doing exponents before multiplication. That's going to be 8 minus 3, which is 5. The first point I'm going to graph for the top piece is the point 2, 5. I'm going to get an open circle because there isn't an or equal to on the 2. And this is going to be the edge of the graph. It's going to actually be the right edge. Now I'm going to plug in 1 and go 2 times 1 squared minus 3. Do the exponent first. 1 squared is 1. I get 2 minus 3, which is negative 1. The next point I'm going to plot is the point 1, negative 1. And then the last thing I'm going to do is plug in 0. I'm going to go 2 times 0 squared minus 3, which is 2 times 0 minus 3, which is 0 minus 3, which is negative 3. And I'm going to plug in the point 0, negative 3. I'm going to do this graph on its own sheet of paper so that I have room to show the work. So I'm going to plot those 3 points. Start off plotting the point 2, 5. Open circle, and that's the right edge of that graph. Then I'm going to plot the point 1, negative 1, and 0, 0, negative 3. So 1, negative 1, 0, negative 3. And when I connect these, it's not going to be a perfectly straight line. It's going to have a little bend to it because it's a parabola, and parabolas get these little curves to it. So when I'm doing the graph, it doesn't have to be perfect, but it shouldn't be a straight line. It should have some sort of bend in it. So that's a reasonable picture of the first piece, but it is going to turn back up. Let me cheat. Let me steal this graph from my calculator And I'll show you how to do that because this parabola is a little bit harder. We haven't graphed enough parabolas. I'm going to go y equals. I'm going to graph this function 2x squared minus 3 because a parabola needs to turn back up. And when I graph 2x squared minus 3, I'm going to cheat on my window. I'm going to make my x max in my window be 2. So I'm graphing this function to see what it should look like. So I hit my y equals. I did 2x squared minus 3. And if I want to see the portion of the graph that I'm graphing, I make my window have x's only up to 2. The x min doesn't matter, but the x max does. And when I hit my graph button, that's going to help me do my graph. And it's going to look exactly like a parabola. As a matter of fact, if I change my y's because they were set for another problem and make my y's go to the 10 and I hit my graph, you'll see that this point right here is the point 25, and then it turns around here and goes up forever. So this parabola, I knew it had to be a parabola because of the square. We haven't graphed enough parabolas, but I was able to steal this from my calculator by just typing in the function 2x squared minus 3, changing my window to have an x max at 2, and this will show me the portion of the graph that I need. So that's part of what I have to graph there. Now I'm going to do the middle piece. The middle piece is also a parabola because of the x squared. And I'm going to steal the graph from my calculator maybe again as well. So the next piece I'm graphing is k of x equals x squared. And this is for x is 2 is less than or equal to x. X is less than or equal to 4. I'm going to plug in the numbers 2 and 4 because those are the endpoints. And then I need 3 points, so the only number between 2 and 4 that's nice is 3. So I'm going to get my points. I'm going to plug in 2 for this x. 2 squared is going to be 2 times 2, which is 4. I'm going to plug the point 2, 4. Because of the or equal to here, I'm going to get a solid circle. And then I'm going to plug 3 in. 3 squared is 9. I'm going to also graph the point 3, 9. And the last one, 4 squared is 16. I'm also going to graph the point 4, 16. It's an endpoint, and the 4 has an or equal to, so it's also going to have a solid circle. Let me show you on my calculator how this graph is going to look, this portion of the graph. So I'm going to graph the function x squared. I'm going to change my x min to 2, my x max to 4. I might have to tweak my y's a little bit to get up to this 16. So if I go y equals, change the function to the middle function x squared that I'm going to graph, change my window, my x's need to go between x, the smallest x is 2, the biggest x is 4. The y's need to go up to at least 16 because this bottom point has 16 for the y. Let me put 20 for it. And when I hit my graph here, this is what the middle portion of the graph is supposed to look like. And this is starting at that right there is the point 24. I'm not even seeing now the y-axis, and this point right there is the point 416. So I'm going to plot the point 24 with a closed circle, the point 39, which is probably going to be about there, and the point 416, and I'm going to connect them. And so this is not even showing the x-axis. This is just showing the segment of the graph that I need to display. So the points that I need to show are the points 2, 4. The point 2, 4 is about here, and then the point 3, and then I'll call this point 39, and the point 4, and I'll call this up here 16. I'm not being super accurate, but it's good enough. I'm going to connect those 3 points with a curve of sorts. Make my graph go through the curve. And that's the second piece. Let me put the first piece back on here so you can see how they look together. But I'm not going to blow up the window. So 2x squared minus 3. Oh, so this should be, let me hit graph. You might not even see it then. Oh, this is, so my point right here is just directly under. This point should be direct, and it should be a solid circle too. I should have an open circle there. It should be right there, directly underneath this, and it pulls over for what it's worth. That's not the best picture in the world. I'll graph this on my graphing computer program in a second to give you a nicer graph, but this is the idea. I'm graphing in pieces. The first piece I graphed had those 3 points. I cheated on my calculator to get a better look. This graph had this 3 points. I didn't really need to cheat on my calculator, but I could have. The last one I need to worry about is 5x minus 7. I'm picking for values greater than 4, so I'm going to pick 4, 5, and 6. When I plug 4 in, I get 5 times 4 minus 7, which is 20 minus 7, which is 13. That point for this function, the point 413, is going to get an open circle because of no or equal to on the 4. And then I'm going to go 5 times 5 minus 7. That's 25 minus 7, which is 18. And then last piece, 5 times 6 minus 7 is 30 minus 7 is 23. So I'm going to graph the point 413, open circle, 518, closed circle, 623, closed circle. This is a line because there's no square, so those 3 points I'll make line up on a perfectly straight line. And that 413 is the left edge of my graph. So to finish up the graph, I find the point 413, open circle, maybe it's about here, it's directly under this. And then the point 518, which I can maybe do okay. And then the point 623, which is maybe up here somewheres. And this portion is going to go on forever. So I get 3 distinct points: the parabola, almost the whole parabola, the arm of a parabola, and then a line. Let me show you how to graph these on my graphing computer program. You're not going to be able to hear me well because I got to walk away from the microphone, but you'll be able to watch me type in the functions, and you'll see me plug in numbers to show the bounds on the functions. So I'm going to do the first function, which is 2x squared minus 3. And that's only good up to 2. Now I'm going to click OK. So that's the first graph that we did. That's the 2x squared minus 3 up to 2. That's this. No, you can't. I just messed up. So I started doing my graphing without turning my computer on so you couldn't see what I was doing. So now I'm going to graph the top function, 2x squared minus 3, and show it only up to 2. So that's the first piece that we drew. That's a big portion of the parabola. Now I'm going to plot the middle one, which was x squared, between 2 and 4. So that shows how, basically what I kind of showed for the first 2 pieces. I didn't do quite as well as my computer. And now I'm going to do the last piece. And for the last piece, I'm going to have to make the window go a little bit higher because my window only goes up to y equal to 10. And it needs to get up to like 18. So I'm going to make the window go higher and graph the last function. Which is 5x minus 7 from 4 and bigger. So now you can see a much better representation of the graph. When I pull my my graph back up, it looks, for me, it looks a heck of a lot like that. I can't do much better, unfortunately, with my limited graphing abilities, and I wouldn't put something that's so kind of subtle on the test. If I have you graph a piece function, it'll probably be more like the first two, where the pieces are really distinctly separated, and the shapes are probably just lines just to make it easier. But that picture that you're staring at right now, that's the optimal picture. It has the first function less than 2, the middle function between 2 and 4, the last function bigger than 4. The problem with that graph, I don't have the open and closed circles that I should have marking the endpoints, and I can't get both open and closed circles to show simultaneously, so that's the graph without the circles, for what it's worth. All right, so again, so this was my graph. If you rewound for a second and looked at the graph that I showed on my computer, they're not that different, and for not having graph paper, that's, this is well more than good enough. So that's the end of the graphing problems. So if I sneak a piecewise function on the test, it's probably going to be just a couple of lines, because that's a little bit easier to do than the parabolas. And it's easier if a graph has 2 as opposed to 3 pieces. 2 word problems that we need to deal with, and I found these online just because I thought they were at least moderately relevant, and although this is from 2005. But anyways, the tax table, if you were doing your taxes and you went to the post office and picked up the book that has the tax forms in it, usually there's a table that tells you how to compute your tax somewhere in those books. And this could have been a table lifted from the IRS's website or from some book that you could have gotten 7 years ago, unless this isn't 2012 anymore and it's 2015, then 10 years ago. But anyways, this is taxes are a classic piecewise function, because it's the more you make, the higher your tax stat. So if you make $28,000, at least back in 2005, you'd pay 10% federal income tax on what you made. If you make, say, $29,000, the first $28,000 gets taxed at 10%, the last $1,000 gets taxed at 20%. If you made like $65,000, the first $28,000 gets taxed at 10%. This is $32,000. The middle $32,000 gets taxed at 20%, and then the last $5,000 between $60,000 and $65,000 gets taxed at 25%. The word problem says make up a function to model this situation, and believe it or not, that function is going to be remarkably similar to the function that I created for pay right at the beginning of class, where it's going to have multiple levels, and the levels that aren't the first level, there's going to be a subtraction in the function to figure out your taxes. So this particular function to figure out the taxes of somebody that makes between $0 and $200,000 has to have 3 levels, because there's 3 different tax rates. And each level is going to have an if for what income it's good for. The first level is, so I'm going to make a T of X. So a T of X standing for taxes based on X dollars of income. I'm going to make it have 3 levels. The first level is going to be good if your salary's less than or equal to $28,000. Once it gets over $28,000, $28,000 and a penny, your tax rate goes up on that last penny, and you pay 20% or 15%, 20% tax. For the first $28,000, my tax rate is just 10% times the amount that I earn, and that's all that it is. For the second level, you pay $2,800 for. So if you make between $28,000 and $60,000, so if my income is bigger than $28,000, but less than or equal to $60,000, I'm paying for any income over $28,000, I'm paying 20%, and this tells me how to come up with my formula. If you're in this earnings bracket, you pay $2,800 on the first $28,000, and then 20% of any amount over $28,000. Here's where the subtraction is going to come in. So my tax, if I make between $28,000 and $60,000, I pay $2,800 on the first $28,000, and then I pay 20% on any amount over $28,000, and the amount over I'm not going to have room here. The amount over $28,000 is my income that I have, less $28,000. So just like I did with the salary, my pay was $15 an hour for any hour over 40, and I did X minus 40 to see how much overtime. This X minus 28,000 is how much money I've made, not over 60,000, but over 28,000. The last line I'm going to do is if my income was between $60,000 and $200,000, and so this is going to be good for incomes greater than $60,000, but less than or equal to $200,000. And it says your tax is $9,200 plus 25% of the amount over $60,000. So I'm going to do this. It's $9,200 plus 25% of the amount over $60,000. The amount over $60,000 is my wages, subtracted $60,000. So these piecewise functions for overtime pay, for computing taxes, generally the top line doesn't have a subtraction in it, but the second and third lines, you're usually subtracting your income minus the level of where the tax changes, or the level of hours where my income changes. So this is a function that's going to model 14 perfectly. That's what's asked in question A. Write the defining rule for a piecewise function giving t of x, giving the tax owed by a person whose taxable income is x, where their income is less than, I'll say less than or equal to, I should probably say, yeah, less than or equal to 200,000. Part B just wants me to use this function to figure out a tax. So part B says, if somebody made $50,000, how much tax are they going to pay? Well, if somebody makes $50,000, their pay is between $28,000 and $60,000, so I need to use the middle function. I'm going to go T, this is doing part B, of 50,000 is going to equal to $2,800 for the first $28,000, and then I'm paying 20% on any amount over $28,000, which is the difference between the $50,000 that they made and the $28,000 that's the beginning of this tax rate. Let me write this better. So the amount of tax they're going to owe at $50,000 is $2,800 for the first $28,000, and then the amount over $28,000, the difference between $50,000 that they made and the bottom of this tax rate, $28,000, the extra $22,000 is going to be taxed at 20%. So the $2,800 on the first $28,000 plus 20% of the amount over $28,000, and that's $22,000. Use my calculator now. Oh, I guess I did. So on the first $28,000, they paid $2,800 worth of taxes. On the last $22,000, which is the difference between $28,000 and $50,000, they're paying $4,400 in taxes. When I add those two amounts together, the amount of tax that they pay at the 10% rate plus the amount of tax that they pay at the 20% rate, that's going to be their total tax bill in 2005 if they had that much taxable income. So the answer to part B is they're going to pay $7,200 in taxes. The next problem, I made a salary problem up just because I thought those were easy to understand. And I made it a little bit different than the introductory example. I made it slightly more complicated. What I did is said, this is how you're going to be paid. You're working for a company, you're making hourly wages. If you work up to 40 hours in a week, you make $10 per hour. Between up to 50 hours a week, you get time and a half. So between 40 hours and 50 hours, those hours are time and a half. That's going to be 50% time and a half is going to be $15 per hour. So this says for up to 40 hours, you're making $10 an hour. And then if you work between 40 and 50 hours, those hours are at $15 an hour. And then if you're over 50 hours, you get double time, and double $10 is $20 an hour. So for instance, if this was, and this is not part of the problem, but this will help you understand the problem. So if this was the company, if you worked 30 hours, you wouldn't get any overtime. Your pay is just going to be $30 times $10 an hour. It's going to be $300, less taxes. If you worked, let's say, 45 hours, then it's going to be like this. You're going to get 40 hours at $10 per hour, and then 5 hours of overtime, but this isn't the best overtime, it's just time and a half, 5 hours at $15 per hour. So you'd get $400 plus $75, or $475. If you worked, let's say you worked 60 hours, then you'd get 40 hours at regular pay, $10 per hour. And then between 40 and 50, those 10 hours between 40 and 50 is at $15 per hour. And then between 50 and 60 hours, those last 10 hours are going to be at double time, $20 an hour. So this is for the first 40 hours. This is between 40 and 50 hours that you're making $15 an hour. And this is between the 50 and 60 hours that you're making $20 an hour. So you'd get $400 regular pay, an extra $150 of time and a half, and $200 of double time. That's going to be $750 worth of pay. So that's how this salary is designed. And I need to come up with a 3-layered piecewise function that would allow me to do these computations so that I could use the function to figure out if I work 30 hours that I made $300, if I work 45 hours that I make $475, if I work 60 hours that I make $750. Hopefully this isn't humbling, but it could be because it's a word problem. So I'm going to do this. I'm going to say P of X to stand for pay, and I'm going to make a 3-leveled piecewise function. The first piece is going to be 10x, and that's for working up to 40 hours. If I work over 40 hours but less than 50 hours, so if I work more than 40 hours but not over 50 hours, I'm going to get my full 40 hours worth of pay plus my overtime. My full 40 hours worth of pay is 40 hours times $10 per hour, so it's going to be $400. This 400 is just $10 an hour times 40 hours. And then I'm going to get overtime. The overtime is going to be the number of hours I have over 40. And I'm going to take my times $15 per hour, because this middle wage is at time and a half, which is $15 per hour for any hours over 40. The last level is for working more than 50 hours. And if I work more than 50 hours, I get $400 for my first 40 hours for 10 times 40. And then between the 10 hours that I get time and a half, 10 times 15 is 150. So my base pay, the pay that I'm going to get is $550 regular pay plus time and a half. And then I'm going to compute my double time. My double time is $20 per hour times any amount of work over 50 hours. So that would be the perfect formula to do this computation. To figure out how much I pay if I work 50 hours, that's easy. I'm just going to plug 50 in for that X right there. I'm going to get $400 for the first 40 hours plus $15 an hour for my overtime. And that's going to be 10 hours of overtime at the higher rate, because the difference between 50 hours and 40 hours is 10 hours. So this is going to be 400 plus 150, and it's going to be 550. So the answer to part B, how much money I would make if I worked using this formula, if I worked 50 hours, this could be 550 bucks. Let me show you that this formula will work for 60 hours worth of work. The formula I have for 60 hours worth of work says this, that I'm going to get paid 550 plus 20 times x minus 50. So for this particular computation, to see if this formula works for somebody working 60 hours, I'd plug 60 in for this x. I'd go 550 plus $20 per hour times anything over 50 hours. 60 minus 50 is 10 hours over 50 hours. That's going to be $550 of regular pay, time and a half, and then $200 in double time would have given me the $750. This is the kind of word problem that if I snuck it onto the test, the part B, asking how much you make, almost everybody could get how much you'd make, but not everybody can create the formula. So if this was a test question and it had a part A and a part B, part A saying develop a formula, part B saying use the formula to get the answer, if you did the part B and got the answer of how much you're going to get paid, you'll get credit for that, but you'll lose points for not coming up with the functions. You'll notice that both of the piecewise functions that I created, they both had 3 levels, but they all kind of had the same flavor, where I had to multiply a salary or a tax rate times an x minus some quantity, and that quantity that I subtracted was kind of the boundary, the bottom boundary at those figures, or those levels. Guaranteed that if I sneak a word problem from this section, that's just going to be one of the word problems that's in this section with the numbers changed. So I won't make you do anything that's a big jump from what I have written in the section. So if you could do all 4 word problems that are in the section, the 2 evens and the 2 odds, you should be fine. So if I was writing a test question and I included a word problem from this section, I might do something like this. You are paid, $20 an hour for regular time, and maybe I might make the rest of it stay the same. And then I'd say write this information in a piecewise defined function, and then you'd have to figure out how the 20 is going to change everything, because your time and a half is going to go to $30 per hour, your double time is going to go to $40 per hour, and then everything else might stay the same. I might change this to, how much would I make if I worked 70 hours in a week. But the words will be exactly the same. I won't tweak the words. So if I pick a word problem from this section, I can promise you I will cut and paste the word problem into the test, and I'll just change the numbers. So in this case, the only numbers that are really relevant is the salary and the number of hours in part B. I'd probably even leave the rules for working up to 40 hours and working between 40 and 50 and over, just so it's not going to be too complicated. Word problems are tricky, so visit me, see a tutor if you're having problems with the word problems. If you need me to make up more word problems for you, send me an email, and I can easily, send you sample test questions I would just cut and paste this particular question into your email, and I'd change the dollar amount or the hours, and I'll give you answers to tell you, so you can test yourself to see if you could reproduce this work by yourself if it was going to be on a test. All right, so that's that section. Just 2 more sections left in this chapter. Section 3.6 is all word problems. I kind of hold your hand pretty tightly through the word problems, so hopefully they aren't too bad. And then section 3.5, you'll definitely want to have your graphing calculator. It's an insanely long section, but one thing that's nice about it is there's absolutely no algebra. You can do the entire section without doing any factoring, any solving for x. For that matter, I won't even have to add 2 and 3 in that section. There's no algebra whatsoever in that section.